Part 3 of the session looks at solutions. So we'll be looking at the components that make up a solution, how you can define a solution as being soluble in terms of one component being able to dissolve in another. Also how solutions are formed, and another related concept of osmosis. So solution is basically a mixture of one or more solutes that are dissolved in a solvent. So the solvent is the component within a solution that is the greatest amount. So usually the solvent is going to be something like water, where there's a lot of it, and it has the capacity to dissolve other components, which are the solutes. So in the examples we're going to be looking at, the solvent is water, and the other components dissolving in that water solvent are solutes such as salt. So we've also got a definition here for the solute, which is the components that are present in smaller amounts within the solution than the solvent. And the solute will actually dissolve into the solvent to create the solution. So we can say that the solution is composed both of the solute and the solvent, and the solute will dissolve into the solvent. So remember, the solvent is the component that there's more of, for example water, and it'll be responsible for dissolving the other component of the solution, like salt. Keep in mind that you can have multiple solutes dissolving in one solvent, but the examples that we're going to be looking at is really just one solute dissolving in one solvent. So we've got an example of a solution on the right hand side here, so we can see a blue solution in the beaker as well as some solutions in the test tubes here. So which would be the component of the solution that's in the greatest amount? Would it be the solvent or the solute? So the solvent is a component that has the highest amount in the solution. What about the solute? What does it do in the solution? Well, it's basically dissolved by the solvent, which gives you the overall solution, which contains those multiple components in terms of the solute and also the solvent. So let's have a look at an example of this. So initially we've got H2O, which is in one container here, and it's going to behave as the solvent, and we've got our solute, which is salt, NaCl, as shown by these individual squares representing a solid piece of salt. So when we tip the salt into the solvent, what do you think might happen? So once we have the solute and solvent mixed together, then we get dissolving of the solute in the solvent. Remember, there's more of the solvent than there is the solute. So in this case, we have a solution forming involving water and salt. So the salt is dissolving in the water, which is acting as the solvent. So here are some examples of other solutions. We just saw solid salt dissolving in our water liquid. So another example where we have this exact solution is the ocean. The ocean has a lot of salt in it, salt water, and that salt is dissolved in water. So the ocean is actually an example of a solution. So another example here is where we have carbon dioxide gas dissolved in water again. So this is actually what we have in carbonated beverages. So any carbonated beverage that has bubbles in it, such as the one shown on the right hand side here, is actually a solution, because the bubbles are actually the carbon dioxide gas within that solution. Air is actually another example of a solution. For example, in air, the main gas is actually nitrogen. So that means the nitrogen is the solvent, and other gases such as oxygen are actually dissolved in air. There's other gases as well, but for simplicity, just showing that the oxygen solute is dissolving in the nitrogen solvent within air. So remember, the solvent is always the component that there's more of, and the solute is the component that there's less of that can be dissolved into the solvent. So we can also work out the amount of solute in a solution by calculating something called the concentration, which is basically just a measure of an amount within a solution. So when you're working out the concentration, you're working out the concentration of the solute, not the solvent. So the component that there's less of is what we want to know how much there is of. So some of the scales that we can use to work out the concentration is we can do it as a percentage. So what percentage of the volume is the solute compared to the volume of the whole thing? So for example, if you put 10 mils of ethanol, which remember is the component present in alcohol, if we put the 10 mils of ethanol into a beaker and put 90 mils of H2O, which would be the solvent and which would be the solute? So the one that's of greatest amount is water, so that's the solvent, so we'd have the ethanol dissolving into that solvent there. So the percentage of the concentration, it would actually be 10% ethanol. So 10% of the volume is ethanol. So 10 mils in a total volume of 100 mils is 10%. So that would be a volume per volume percentage. You can also do a weight per volume. So how much does the solute weigh as a fraction of the complete volume? So for example, as an example here, if we dissolved 1 gram of sodium chloride into 100 mils of water, we would say then it's a ratio of 1 to 100, so that's a 1% weight per volume solution of sodium chloride. So we can also use something called molar concentration or molarity, which is basically relating the number of mole of your solute to 1 liter of solvent. So how many mole are present per liter? So we don't actually calculate this in the course in terms of the molarity, but you can actually use the periodic table to work out the mass of the particular component and relate that to the number of moles it's going to have in solution. So there is a way to calculate that. Also, another way of working out concentration is number of parts per million. So a part per million means you've got 1 part solute per 1 million parts of solvent. So this is equivalent to milligrams per liter. So if I put 1 milligram of salt into a liter of water, that would be 1 part per million. So we can describe the amount of solute that can actually be dissolved in a certain amount of solvent, and that is basically the solubility of the solution. So the maximum amount of solute that can actually be dissolved in the solvent is a measure of how soluble the solution is, or the solution's solubility. So, for example, at 20 degrees, roughly 36 grams of salt can actually be dissolved in 100 mils of our water solvent. But if you add any more than that, then the salt will no longer dissolve. So that means the maximum solubility of 100 mils of water is actually to dissolve 36 grams of NaCl. There are different factors that can affect solubility though, including temperature, which will actually allow more of the solid solute to dissolve in liquid. We can also adjust the amount of the solvent. So if you add more solvent, then you can dissolve more of the solute. So that would make your solution more soluble. The polarity also has a big part to play in how soluble a solution is, because they have to have matching properties in this case, because polar solutes will only dissolve in polar solvents. Same with non-polar. If you have a nonpolar solvent, you have to be dissolving a nonpolar solute. If you have a component that is polar with one that's nonpolar, essentially they don't mix. And this is what we see when you put a solution of oil into water. They don't mix because the water is polar and the oil is not. Whereas when we mix polar salt with polar water, then we get the mixing happening to create the solution. Another definition for us is a saturated solution. So this is what we describe a solution as after it's reached its maximum solubility. So once the solution has dissolved its maximum amount of solute it can, we then say it is saturated. So if we look back at the previous slide here, we can relate this to the example here. So here we said that 100 mils of water could dissolve 36 grams of salt. So if the solution had already dissolved that 36 grams of salt, it would now be a saturated solution because it's dissolved the maximum amount of solute it can. Interestingly, if any more solute is added to one of these saturated solutions, then the solute actually won't dissolve at all. It'll remain as an undissolved solid. So going back to this example, if we tried to add another 1 gram of NaCl, what do you think would happen to that salt in that saturated solution? Would it dissolve or stay as a solid? Because the solution is already saturated, it can't dissolve anymore, therefore it's going to remain as a solid. There are ways we can change our saturated solution into a non-saturated solution, and that is by increasing its solubility by either adding more solvent or increasing the temperature. Alright, so let's now have a look at an animation that will show us what we mean by a saturated solution. Okay, so at the beginning we've got our H2O solution and we've got some salt. So first things first, let's try and add some of that salt into our solution and see what happens. So because the solution hadn't had any salt added into it yet, we can add in some salt, dissolving that solute into that water solvent. Let's add some more salt in this time. Again, it dissolves. So after adding a certain amount of salt, we've now actually saturated the solution. So what does it mean now that our solution is saturated? Basically, it means that the solvent has dissolved its maximum amount of solute it can. So it can't dissolve anymore. So what about if we try and now put more salt into that saturated solution? What's going to happen? Well, now that it's saturated, essentially it can't dissolve any more of the salt. So the salt will actually remain undissolved as a solid form. So you would actually see the salt as a solid even though you've added it into the solution once the solution has been saturated. So let's just have one more look at how this works. So initially we have a solution that's not saturated, dissolving salt in that solution, and then dissolving another lot of salt again. And then after dissolving that second lot of salt, we've now saturated the solution. So if we put any more salt into it, that now means that the salt won't dissolve. The solute remains as a solid due to the solution being saturated. So now we're going to go into the technicalities of exactly why the polar water solution, the solvent, can actually dissolve the polar solute, which is the NaCl. So remember that each water molecule can have. So for each water molecule, it's got these two polar covalent bonds connecting the oxygen and hydrogen atoms. So this means that we've got this distribution of charge where the electrons are more attracted to the oxygen that we show as being partially negative, and the hydrogen has less association with those shared electrons, therefore it's partially positive.